Um, and so we mostly talked about one mode of ext3, namely the journal mode, where both the file system blocks and the metadata blocks are actually put through the journal. And what we've seen a lot in the lecture so far is that one goal, or one overriding challenge, with making a logging system. The logging system is great in terms of recovery, right? It makes it very easy to recover from after the failure because you can just replay from the log. The main challenge with the logging system is trying to get good performance. And if you've seen in the paper, ext3 goes through quite a bit of lengths, to actually get good performance. So first of all, for example, almost never the log is actually written or read, during normal operation. The only time that the log actually gets read is during recovery. But during normal operation, the log is not read at all, unlike the XT6 log, for example. But by stressing or pushing on performance, there's a big impact or increase in the complexity. So, for example, one thing that ext3 does is that when it actually commits a transaction, writes the commit record of the transaction, it actually doesn't immediately update the file system data structure itself at all. And in fact, it postpones that to sort of a later point in time. And that's sort of a stepping stone for like a little set of little things that actually amount to more and more complexity. Because that means that if you cannot commit T2 if T2 at some point is done until after T1. You cannot update the data structure due to T2 until T1 actually has updated the file system. So you get some ordering constraints if T1 should go before T2. But they also want to allow that T1 can update the internal, or T2 can update the internal data structures or blocks that may be written by T2. They want to allow T2 to update internal buffers in memory that were written by T1. And the reason that's a little bit tricky, because that means that the point that T1 wants to commit can actually not commit anymore with the modified buffer, because that was actually modified by T2. So it cannot write that to the disk. So that means that if you actually commit T1, you also have to commit T2. And so that forces this. Or you cannot install until you also committed T2. So there's another rule, basically, install only if T2 or any dependent transactions are committed. That's all fine and well. But what happens if actually the log is not big enough to actually commit T2, right? And we saw that introducing yet another set of problems, and the way that ext3 solves that is actually by reservation. So hopefully that at least brings back ext3 back in your head, but it also sort of shows you that by just going for performance, that the complexity increases very, very rapidly, and sort of these corner cases that you have to think about get quickly tricky. Now, the result is, though, from sort of design like this, that ext3 does get very good performance. Right? And for example, if you create 100 files, like we computed out last time, that if you were writing 100 small files, creating 100 files from like one block on XT6, it's going to take about 10 minutes, correct, in order to actually create that. Or 1,000, I don't remember the exact number, but you could compute it out. It adds up very quickly because it's about 10 seeks per operation, per create file. And seek is in 10 milliseconds, so 10 of them. It's 100 milliseconds, 100 files, and then you get 10 seconds. So it's 10 seconds. And that's notable. In ext3, how long it will take? For example, let's say we're writing 100 files in a single transaction. And we want to make sure that at least the state is on the disk. Well, it's not going to take that long, right? Because they're going to be all sitting in they're all going to be sitting in memory, and they just happen to be written sequentially to the log. And so basically, the transaction pick up all the 100, all the dirty blocks, and pick them all together, and write them in a one big operation to the disk. And so that's going to be like some metadata blocks plus, say 100 or 1,000 data blocks. But the disk bandwidth or from solid state disk in for magnetic disk is really, really high. So in fact, you can write at the rate of sort of 50 megabytes per second. So if you compute it out, actually writing all the data at 50 megabytes a second comes down to roughly 10 milliseconds. So this cost of one seek, basically, you can write all the data to the disk. Presumably, then there's one more seek to actually write the commit record to the disk, but that's it. And so you're done in basically 20 milliseconds. So there's a huge, huge, huge improvement over the speed. Now, users of HT3 actually want to do even better than that. And so therefore, there's a second mode, which in fact most HT3 installations probably run in that mode, which is called order mode. And in order mode, HT3 only writes metadata blocks. Blocks for metadata. Right, so the regular data block, so if you create a file, then the data block of the file is actually not written into the log when you need to flush. You need to commit, but only the metadata blocks are committed or written into the log at commit time. And the metadata blocks, again, are the inode, things like that, or the blocks that contain inodes, or a directory that actually points to that particular inode. And clearly, the advantage of this scheme is that you don't have to, the downside of actually writing things in the log is that you, at some point later, you do actually have to update the file system. And so basically, you're writing every data block twice, once through the log and once through the file system. And by not writing the data block into the log at all, you don't have to, write the data twice, right? You can write it once, you write it immediately into the right place. You write it immediately to the file system. Now, you've got to be careful with that, right? Because, the goal is to recover it correctly. And so you have to make sure that that everything will work out correctly. And so there's a lot of risky, sort of there's an additional set of rules that you have to follow to make sure that everything works out. For example, if you write a file and you want to put the new modified inode into the log and you want to commit it, then you have to make sure that whatever inode, whatever blocks that inode is pointing to are actually on the disk, right? Because otherwise you might be, you write an inode out with some block numbers in it, and those block numbers might contain not the data from your file, but some other file, for example, etc. password or something like that. And so it's important that you follow this approach, along with the metadata. Then you have to write the data blocks before you write the log. And this is why it's called ordered mode, because it actually that's the basic rule that you have to follow. Basically, anything you write into metadata is going to point to data blocks. All the data blocks have to be on the disk before actually you're writing anything that points to it. But if you think a little bit about this, there are going to be tricky cases, right, where things are problematic. There's quite a number of them. I'm not going to go through all of them, but you immediately should make clear to you that basically by doing this, actually going for even higher performance, you get even more complexity. The more cases you have to think about. So let's take just one to get a little bit of a sense. So here, case, and of course all the tricky cases follow by come from the fact that basically there's an inopportune time when the failure happens. And so here's one. You do a remove there. You remove the directory with all the blocks and all the files that are in it, so that creates a lot of, in principle, free blocks. Right? But you do all this update internally inside of the buffer cache, not on the file system yet. So basically, that frees up a bunch of blocks. And so let's say that we use one of those blocks that was complete. So we use a block B for a file F. Let's say you create a file after you remove that directory. Right? So those blocks are available in principle. Now, that file is also being created in memory, so no problem at all yet. Right? So everything is actually in memory. So everything, if now we had a failure, we have written nothing to the disk, so we'll be stale in before anything has happened. That'll be fine. So far, so good. But let's say at some point we want to actually write the file to disk. Right? And so to be able to write the file to disk, we have to do an ordered write. because we have to make sure that we want to put the inode the file f into the log. Then it means that we have to put the data block that f is pointing to, actually onto the disk, right? So first thing you need to do is we need to do an order write for B, right, before we can actually put anything in the log and commit the log. Now once we've done the order write, then just unfortunately for us, we could just have a crash right here. And now we have a problem, right? Because we have updated block B, so we have modified block B now. And whatever it contains, whatever data that the file, the new file F actually contains, we crash, and we have nothing in the log. Right? We actually have no remover in the log yet. We have no create file yet in the log because we have to do those guys first, because otherwise we have a problem. And so we could actually run into we could have this problem now that if we recover, we'll come back with the directory not being removed yet. But now blocks that were used to actually make the directory actually contain the content of the file F. And so basically we have a garbled directory. Right? And so we can't do this in this way. We have to be more careful, correct? So there's basically a set of other rules that we have to follow in addition to this ordered write rule. And so one rule, so the way ext3 solves this problem is to say, well, we're actually, we don't really free blocks. You delay a free, actual free, until the operation that actually freed the blocks actually is committed. Make sense? So the more cases like this, I think in the lecture notes I have a whole bunch of those. And then each of one of them actually introduces yet another rule that needs to be followed to make sure that actually correctness is maintained. All to get this sort of both high performance and the correct implementation. So in fact, in the end of it is that basically ext3 is a pretty wickedly complicated, file system, right? So I'm not going to go for all these other, example cases that are complicated. You can look, if you're curious, you can look through lecture notes, but they're all follow this kind of form where you do something just before the last final step of operation, your system crashed, and now you have a problem. Because you can't recover correctly, and so you have to introduce an additional set of rules that protocol rules that the file system implementation has to follow. Yeah, go ahead.
Doesn't this violate things because we're actually writing data to disk before it's committed?
Yeah, so in order mode, you already have to buy into the fact that your data blocks are not protected, right? And for most, and so the main goal is to actually at least make sure that the file system, internal data structures are correct. So recovery will not guarantee in order mode that actually you recover your data blocks correctly. The only thing it will guarantee is that it should guarantee your directory should recover correctly. And this is a problem, right? Because in this scenario, the directory actually doesn't recover correctly. Yeah. So in order mode, you already, as a user, you already decided that you don't care really about the data blocks being 100% to get better performance. You get something in return. You lose something, but you get something in return. And a lot of people run ext3 in ordered mode. It's a pretty common way of running it. Any further questions about this? Okay, good. So then, the total switch of topics, and talking about OS organization, and a lot of the discussion of OS organization. A lot of discussion of OS organization comes down to what is the right kernel API. And so let me start there. So the goal, is to get a good kernel API. the reason that we want a good kernel API is because there's an assumption that you can't change it. So you basically get like one shot at it, but once your sort of operating system is in production, right, the kernel API is set, and you can't really change it. So this is going to require a slightly mindset change for what you're doing, right? Because you're in charge of the kernel and the libraries and the applications, and you're like, I want to change the kernel API. Well, give me Emacs or Vim, and I'll change it, correct? Because you can implement whatever you like, but no, in real life, that's not the way it works. There's a small number of people that are actually in charge of the kernel, and nobody else is. And so if you want to change the kernel, you got to talk to the small number of people that are actually in charge of the kernel. There might be a large group of people in the case of Linux, but it's still, there's some set of people that own the kernel. And it's not strange, correct? That's the case because that's the trusted code. Like if the kernel is wrong, then everything is wrong, and so you want competent people to actually update, maintain the kernel. And so there's a discussion about like what is a good kernel API is highly relevant in a world where there's a small number of people actually in charge of the kernel that can modify it. Right? And so you should totally sort of put out in your mind like what you currently are doing, which is like you're in charge of the kernel, you can do anything you like, and you don't have to convince anybody. Right? So what could we look for? Right? Like what are the things that will actually might just get us excited about your thing is a good kernel API? And there's something clearly at this point you should be reasonably qualified to discuss, right? Because you have been thinking about this and you've been implementing it. So one, I'm going to throw out some goals. One goal is that that apps are easy to develop. The people that are going to run or use your kernel API are application developers, and it'd be nice actually if their job was not painful. And so that argues for some way or some high-level API that takes a lot of care of the details, correct? On the other hand, apps should have can use hardware resources. And clearly, the reason you're running applications is because you want to benefit from the hardware resources that are sitting in the machine, whether it's like the CPU or memory, network interface cards, whatever feature actually sits in the hardware. Hopefully it will be visible and usable by applications. It'd be too bad if the hardware has some cool feature, right? Basically, the kernel API forbid you to use it because it just was not exposed to the applications. Finally, sort of a couple other things that we clearly want to get out of it, which means your main themes of API. You want apps multiplexed, and multiplexed securely, correctly, sort of isolated. Like one app fails, and another app doesn't fail too. But you want to multiplex in an isolated way. And we've seen that a lot of the complexity, a lot of the mechanisms that we've discussed in the last couple of weeks all come from this sort of isolation goal. Right? In fact, a lot of the hardware or the x86 machinery you're programming has all to do with isolation. That's why you have virtual memory. That's why you're having your CR3 and why you have to get all that stuff right. On the other hand, you also want to be able to control sharing. So it should be possible for applications to communicate with each other and be able to share. In Unix and the x86, we've seen pipes as a way of doing it. In Black 5, we were seeing sort of an IPC primitive to send little messages from a client library to the file server. And then there are a couple more goals. We want few kernel crashes. Too bad if your machine fails, if the kernel fails, correct? So it's clear it's a good goal. This some way argues that kernels should be small because if they're big, presumably there's a higher likelihood that there are bugs being in it, and if the bug gets stricken, they fail. And then the final goal that you probably want to have is the kernel should be involved. Even though I say like the API, can't really change the API. You can certainly evolve the API over time. Right? It may go slowly, but you're certainly going to be able to do that. And so these are sort of, if you will, sort of a very high level, sort of ideal properties that we might want to have from a kernel. And we're going to sort of look at these different organizations, the monolithic, microkernel, exakernel, sort of see, how well or like how they deal with this set of goals. Right? Clearly, they're conflicting a little bit. One are, before making applications easy to develop, argues for high-level interfaces. That probably high-level interface means probably more code in the kernel. Right? You have to implement these high-level interfaces, so there must be some code that implements it. But that probably means, maybe you're running at the risk of more kernel crashes. And so, one thing that makes this whole discussion complicated is that there's really no evidence, or not much scientific evidence, either arguing for one of these approaches is the right one. So there's a ton of religion about, what is the right way of doing things. Like almost most discussions about APIs, right? And certainly, if you go to an OS conference, you want to get people excited about something, you say something outrageous about either microkernels or monolithic kernels, and you will at least offend one half of the audience. Yeah, so there's certainly among OS developers, a highly beta topic. Yeah, go ahead.
But if we have such goals, what is the reasons to choose monolithic way to construct the operation system?
So hold that question and let's go through some more detail, and then we'll come back at the end. Why choose one or the other? And at that point, hopefully, you can argue any end of this debate. So okay. So let's start with sort of quickly reviewing these different organizations. So monolithic we have seen in action. Basically, you can think about XV6 as being sort of a very clean version of an analytical system. You can think about Linux as a monolithic system because certainly it's a big kernel. And so what is the general rule there is that the kernel API is roughly equal to the cost of Unix. And so there's system calls that monolithic systems sort of support are of the form open file, read file, write file, create file, create a process, pretty high level, like fork, exec, all that kind of level of system calls, right? Which is very different than the API that you're implementing, for example, in the labs, right, where the system calls are definitely not, fork, exec, at that level. Okay? So what is good about this? Well, clearly one advantage, of a scheme like this is very easy for developers. Maybe not easy for kernel developers, but very easy for application developers because they get a very high level API they can program with. Like if you give an application developer the JOS API, there's like XO fork. So here's XO fork. Please go and write an application with it. The first thing they're going to do is they're going to write a bunch of libraries to actually make the API much more usable to use. Right? And so, while the Unix APIs was fork, which is a much more general, higher level primitive that's presumably much more directly usable for applications. And so, what does the this API do? You can sort of look at the API in two ways. Two main functions that it has. One, it virtualizes a number of resources. Particularly, it sort of virtualizes the CPU and memory, and through virtual memory, or in the CPU case by transparency switching. And in addition, it does abstracts a whole bunch of resources. So you think about the hardware resources on the machine, some of them are directly virtualized, meaning basically that the same, kernel provides the same interface as the low-level hardware does. And so in the case of CPU, you get instructions, assembly instructions that you can just execute. In the case of memory, you have a big memory from 0 to whatever, and what basically looks like loads and stores, right? That you manipulate it with. On the other hand, there's a whole bunch of other resources on the board or the machine that the operating system or the Linux system will abstract. You don't get actually a raw disk, on a Unix, right? You get actually a file system. And the file system has all kinds of other new neat features that the raw disk doesn't have, like directories, path names, and all that kind of stuff. So you can think about this. So I'm making this distinction basically between virtualization and abstraction, where abstraction really builds something, a new abstraction out of some low-level resources. And actually, most Linux systems do a lot of the abstraction. Pipes, as a way of abstracting channels, right? At a much higher level. Windows systems, abstract the display to something that is much more, has a whole bunch of additional properties, right? And the network, you don't get a wire where you can set bits on, right? You get actually TCP, which is like a totally different thing than your raw network, right? So typically in a monolithic system, you'll see a lot of, a little bit of virtualization and a lot of abstraction. And we've seen that in x86. Right? There's a lot of abstraction going on. Now, there's reasons to be sort of excited about this. Because it makes life in the application developer easy, and so let's talk a little bit about that. In what way things are easy. So I'm just going to mostly not talk about abstracting the resources, but mostly talk about actual virtualization, just to make things concrete. So first slide, CPU. We have seen this in x86, and we've seen this in the context of the labs too. I'm just going to quickly remind you, right, what the main plan is. Let's say you have two processes, process A and process B. You have one processor to actually run them on. You have to do some virtualization and wait. So let's say A runs for a little while. Then at some point there's a clock interrupt that comes in. And that gives actually operates the kernel a chance to actually run. It may decide to actually switch the processor, hand it over to B. B may run that for a period of time, and then B may actually at some point do a system call or yield, and then swap back to A, and then A may run for a while. Right? And the yield may be forced, or it may be done unforced. Right? Forced yield happens because when a clock interrupts, it happens it's just like, this is the end of your time slice. You're not allowed to run longer. And there's a whole bunch of machinery, as you know now, there's a whole bunch of machinery to actually make this work. Right? It's easy to draw this picture in the blackboard. Once you have to code it up, actually you discover it's a little bit more complicated. There's a lot of nasty little details that you got to sort of take care of. Right? But from the perspective of the programmer, right, that uses a monolithic system, this is all hidden. It's completely transparent. Right? You don't really see this because what do you see? The system calls you see is fork, kill, and exit. And those are the system calls that actually make a process. You don't see any of this stuff, all this machinery that's all completely transparent to you. Okay, so similar, if you think about memory, the high-level picture is extremely straightforward. And even, there's even more complications there than with CPU switching. Basically every two applications A and B, right? Both of them, get actually the illusion of a physical memory or a virtual memory that's the same as physical memory, right? Going from 0 to whatever 32 minus 1. Right? They can do loads of stores to address 0, loads of stores to any address in that range. Now, not all loads of stores might work, but in principle they can do it because they have the illusion that they have this whole memory. In fact, each application has its own illusion of complete physical memory. Right? And the way that is implemented is by having page tables that record mappings from virtual addresses to physical addresses. And there is one register that points to sort of the active page table, right? The CO3 register. And now in the context of a monolithic system, again, all this stuff is completely hidden. There's the system calls actually that you operate with when you look at x86, and the system calls that you get is basically exit. And that replaces one address space with some further running with the contents of some other the contents of what's on the file and puts it into memory. And there's really no other system calls other than one more. You can actually grow your address space with sgrade, right? You allocate more memory. And that's the two system calls you get. And again, these system calls don't expose any of the underlying machinery, right, that actually the kernel actually uses to implement these abstractions. Now, internally, we know that the operating system does all kinds of cool stuff with virtual memory, right? Because this level of interaction from translation from virtual addresses to physical addresses give you all kinds of opportunities, right, to do cool stuff. And we saw it in we have seen a couple things like that, even in the context of x86, right? VM tricks. So one of them, copy and write. Fork. One process forks another process. Don't create the whole new address space. Just do copy and write, and so that you can mostly, use the same pages as the parent, and only when the child modifies them, you make a copy of the page and actually modify the copy. Right? But before that, you don't really do anything. And those allows you to actually make fork, for example, very, very fast. There's not much involved. You've done this in the context of a library, or you're doing this in the context of a library operating system. That's sort of as a being kernel developer, right? And there are a whole bunch of other tricks. Like, what are other tricks you can do with VM? I'll make this a one-way. Yeah,
Shared memory.
Yeah, shared memory is a good one. You can take a page, right, and map it into two different address spaces so that the two address spaces communicate through that shared page. You would do that in Lab 5. Any other?
UVT, UPD.
Yeah, the dreaded UVPTs and the UVDs, correct? Basically, you can take a whole bunch of part of an address space and make it turn it basically back into a linear array instead of having exposing or having to deal with a two-level structure. Yeah. Yeah, a page out basically, right? Like leave the data on the disk, only load in what you actually need. So page out is a good trick. We're going to run out of space because there's so many good tricks. Right? Like zero field pages. Create one zero page only when you instead of like making many of them, and then map that zero field page, copy and write. So there's like it turns out like inside an operating system, there are all kinds of little cool tricks you can do. But these abstractions from exec and sgrade don't really expose any of that. But you might think, well, why should these tricks be limited to the application, to the kernel? Right? But maybe the application can also do very cool stuff. With having the hands-on sort of virtual memory machinery. Right? And so one problem that this paper addresses, and also with partly addressed in microkernels, is trying to figure out how to sort of take this internal machinery that clearly is very handy to implement an operating system and make that available to applications. And so that applications can do their own cool tricks using virtual memory. And the one way to think about an extra-kernel, so an extra-kernel takes that to the extreme by saying, like, not arbitrary applications. We're going to go so far that we actually want to implement most of the operating system in user space, so that's the application code. Right? And clearly, the challenge, if you think about this for a second, the clear challenge is like how to maintain this whole goal of isolation. Right? If we're going to expose all the machinery to the applications, then we've got to make sure that we don't give up on isolation. Make sense? Okay, so. Before switching to talking about microkernels, I want to say a couple more things about monolithic systems. So in the monolithic system, the kernel API is basically the POSIX API. But I want to talk a little bit about these sort of goals in the context. So what is the answer? Clearly, the monolithic systems do well on this part because they give you a high-level API. What is the solution? Like, what is the solution if there's new hardware resource comes out? How is that made available? So like you buy a new machine, a piece of hardware that has a cool hardware feature, and you run your monolithic kernel on it. That's written by somebody else, correct? And you're not allowed to modify it because it's trusted. What happens?
You have to update.
Yeah, but, you have to update your kernel, which means that somebody else first, correct, has to implement a system call or some feature that exposes that hardware resource, in some form, right? And so the answer to basically new hardware features, or in generally any sort of evolution over time, is that the kernel developers decide, we're going to make a new system call, or we're going to add something to the kernel. And then we're going to put out a new kernel, and then you can download the kernel, and then you can run on your hardware, right? But you can't do it. That's sort of the way of the world to think about it. So it doesn't really, and so it might take a while, right? Because you have to convince the kernel developers that this is actually a good thing to do. And if they don't agree with you, then you don't do it, right? And then you're toast. You have no choice. Now there's a slight way, in practice in Linux you can get around this kind of stuff, because in Linux, in principle, you can actually download code into the kernel. You can actually there's an extensibility mechanism in the Linux kernel where it allows you to basically write arbitrary code and put it into the kernel. Of course, that's then at your own risk. If you make a bug in that code, then there's no guarantees that your kernel will crash, but it's then your own fault. And presumably so there's some mechanism for that. So that's okay. Maybe there's some delay, but presumably at some point the system call will be available. It does a good job of multiplexing and isolation because in fact it doesn't really expose much very low level stuff. The kernel crashes. One argument is that that's not such a good story, right? Because how much lines of code are in Linux?
Millions.
As opposed to x86, right? Because x86 is small. Even x86 has bugs. How many?
Tens of millions.
Yeah, tens of millions, correct? Lines of code in the kernel. Much more than you could write in a single semester. And so there's no. If you have tens of millions of lines of code, written in C, correct? Doing tricky stuff, right, which you're now well aware of. There's likely going to be some bugs. And so you might think that things are not so wonderful. And this is what the motivated microkernel people. They want to really go for it and say, okay, we want as little trusted computing, trusted code as possible. So they organize the system quite differently. Let's go to microkernels. So the microkernel sort of organization style is you have a small kernel, microkernel. And the API that it provides is pretty minimal, because otherwise you couldn't make it small, right? And so the API that it provides typically it has some form of IPC, inter-process communication, being the ability to send a message from one process to another process. It has a way of creating some minimal ways of creating processes for address spaces. So it has some support for creating an address space and some support for creating threads within the address space. And that's sort of the three minimal mechanisms that a microkernel has, and then the rest is implemented as a regular application code. So you will implement the whole file system, you run it as a normal application on top of the kernel and runs a user space. And like an application like the shell, runs also user space exactly as it is on a monolithic system. But when you need a file, you actually send an IPC, you send a message through the kernel to the file server. And asking, please, I want to create a file, open a file, read or write, right? So all the file system instructions of read, write, read, open, etc. All the file system calls are actually not implemented by the kernel, they're implemented by this usual server. Right? And you're going to have, and the general idea is you have servers for every other feature that sort of sits in the monolithic system that you didn't build into the microkernel. Right? So you're going to have your network server that's going to sit here. You may have a server that hitches out part of your, address space, to disk, et cetera, et cetera. Right? And so The damage correct with this organization in principle is that if there's a bug in the pager or the network stack, this user level application may fail, but not the rest of your system. Because presumably, the kernel is so small that you can really do a good job of trying to get this whole correct and make it very, very reliable. Make sense? So now we can look at this list again and sort of think about, well, how well do we sort of stack up, with this microkernel organization against these goals, right? Well, are applications easy to develop? In principle, yes, because you implement a bunch of servers that actually implement the same abstraction as the monolithic system does. So in principle, you can run the same applications. And can the application use hardware resources? Well, it depends on how well you're exposing how low these low-level interfaces. Right? Often, the way it works is presumably is that often hardware resources get exposed through the virtual memory system. Right? I mean, a store loads a read and write to an address, gets a device to do something. Right? And so one way to do that is you give some of these hardware resources to a server. The server actually implements the new API, and you just have to redirect the I/O operations to the server. And so the standard trick is, for example, to have the file server map in the hard disk or the hard disk controller directly through the virtual memory system into only the process of the file server. So only the file server actually owns the ability to read or write to the disk controller. Similarly, only the network server will have the ability to read or write the network card interface and no other process. Okay? So in principle, you can do it. Now that also gives you this isolation goal still, right? Because first of all, these guys are so by themselves by the virtual memory system, they're isolated. But even all the interactions with the hardware resources are carefully managed that only the appropriate user level processes can actually get to those hardware resources. So there's no way of sort of circumventing any mechanism to get sort of full control of the hardware resources. So that's a pretty good story. Of course, hopefully fewer kernel crashes, right? Because the kernel is small. And in terms of kernel involvement, presumably the hope is to get such a low-level API that that's pretty stable, right? And if you want to involve the higher-level APIs, well, that's pretty easy. You just have to evolve to change the user level servers, right? To have the new API. Make sense? So what's so this sounds like wonderful, right? This is exactly what you want. There are some complications. And so, yeah, go ahead.
So what happens if the file system server just crashes? Who restarts it?
Yeah, so that's one problem. So yeah, the kernel is now very reliable, but what about this code? Right? If you don't have a file server, maybe you don't have an operating system. And so it is actually not as simple as I drew on the platform here. And a lot of monolithic people, so this is the first thing they will say, right? Like, great, you put it in user space, but if it fails in user space, maybe slightly better than failing the kernel, but whatever, the machine is unusable anyway. And so it doesn't really matter where, that you put it in a different isolation unit. And of course, the microkernel people will argue, well, now we have all the mechanisms in place to restart it, for example, after a crash, or automatically restart. And then the monolithic system, well, we could do that too, we could just reboot the machine, whatever. And so this is a little bit of a complicated issue. And then there's a larger issue here, right? There's often dependencies between different components. I think that's the most interesting aspect. I mean, if you look at x86, right? The VM system and the file system are reasonable interconnected. In fact, if you look in Linux, they're very interconnected. In fact, there's one page cache that serves as the cache for both pages in the virtual memory system and as pages for the file system. So you could split them apart, right, and put them differently, but then the file server and sort of the buffer cache and page cache have to coordinate, right? Because page cache is just an inherently shared thing. And so it's actually not that trivial. So if you want to, for example, have the VM system in this store in the pager, coordinated their the sharing of their buffer cache, presumably what you need is like another process right on the side, that implements your buffer cache. Or you need to distribute your buffer cache across the different files servers, and then you have to wait to find out where the block is. right? This is all trivial in a monolithical system, right? You know, you look in the table, boom, there it is. It's one single table. And so this is where like some of the complication comes in, and this shows up not in a functionality way, but it shows up in performance issues, right? Where systems get slower because either they have mutation buffer cache instead of a shared buffer cache, or you're doing a lot of IPCs from one process to another process to another process to actually get to the data. So what in a monolithic system would be just a system call and get the page, now it's multiple IPCs. And it's not uncommon that at least monolithic systems that actually or microkernel systems that implement most of Unix and internal server processes are pretty slow. In fact, if you look at the early microkernel literature, it all they build the whole system, they run benchmarks, and then are basically 5 times or 10 times as slow as a monolithic. Factor 2, whatever. Some factors slower than a monolithic system. And so that's the main challenge. Shared resources, management, shared resources across different servers, and performance tend to be an issue. Yeah, go ahead.
So if you wanted to expose like protected hardware to one of these server processes, but it happened that the memory map registers were the same page as another, like a printer and the keyboard on the same page, how do you?
People try to, they explode it, we'll split it up. It's much more fragmented. You won't put the same information on the same page, because otherwise you'll have a problem. Or you have to trust one other process that also maps that same page. Like so maybe the keyboard manager and whatever other manager trust each other to not scribble over their device registers, which is still better than having the whole system be trusted and not scribble over the devices. Any questions? Okay, so then now. So microkernels haven't been sort of a big success in your desktop or your laptops, right? And none of your laptops probably run a microkernel. Is anybody running a microkernel operating system on their? I'd be impressed if you were, but most people don't, right? And so in the server market or the desktop market, laptop market, microkernels have not been a particularly big success. Partly, for many reasons. I'll come back to that later, but they're not as clear. Observation truth. But in other markets, they have been much bigger success. So like embedded systems, you'll find a lot of microkernels. Partially because you don't have to support the full Unix functionality, right? And so it's much easier to get started in a market that doesn't require a lot of features. There are other, so even though like they're not successful on your desktop or your laptop, there are other places where they're commonly used. And there are quite a number of successful microkernel companies actually out there, or microkernel distributions. Okay, so then the last one I want to talk about is basically, you know most about, so I'm not going to talk a long time about it, is microkernel organization. And the first thing to realize is that nobody uses extra-kernels other than you. And so in that sense, putting them in the same list as micro and monolithical is a little bit misleading, right? Because they're much more sort of an intellectual exercise in kernel design than they are a practical artifact. And so the organization there is the philosophy here is where you explore basically the hardware resources. The kernel interface is identical to the hardware interface modulo protection, and it might be slightly different because you need to do protection. And so you have applications, and the application is structured as a library operating system. And since it's all user space, you could have many different library operating systems, right? So you might have your standard Unix library operating system to run LS, and you might have Prime library operating system Prime that whatever is optimized to run web servers, right? Or a database server, or whatever. And this part of the operating system can be totally specialized for that particular application. And then And the hardware, the interface itself, between these, which is the library system and the kernel, is actually hardware specific. And so, for example, if you would run an extra-kernel on an x86, it would run look differently than an extra-kernel running on a MIPS processor. Right? For example, the one in the paper runs on a MIPS processor, and so it will have a slightly different interface than actually the JOS kernel has, which runs on x86. For example, in x86, page tables are built into the hardware. You cannot change the layout of the page table. It's a two-level page tree, and that's just the way it is. The hardware designers decided that that's the right page table structure for you. But on the MIPS, actually the page table structure is actually implemented in software, and the only thing that's actually implemented in hardware is the TOB, the translations look-aside buffer. Right? And so on an extra kernel on the MIPS, you can actually have your library operating systems implement radically different page tables. And when on the x86, you can't, because the hardware is that way it is. Now, both in the monolithic system and in microkernel systems, this interface is not hardware specific. It is a standard interface that's supposed to work across many, many different platforms. And so this is a big, big difference. Right? Exposing basically the hardware research directly to the application. Now, of course, the real problem then comes in, how do you achieve isolation? Right? And so we'll talk a little bit about that. So first, let's talk about it in terms of virtualizing the CPU, which, in fact, in JOS, we sort of cheat a little bit on. But in the system described in the paper, it actually has a different mechanism. So in principle, the description in the paper is like when an interrupt comes in, the kernel doesn't do anything. The only thing it does, it actually does an upcall, like your page fault handler, to user space, saying like, "Hey, process, I want the CPU, and you got to get ready to. You need to do like save your state so that we can do a switch." Right? And then that application then, or the library operating system, presumably is in charge of sort of squirreling away the registers that need to be saved, or like making sure that all the calls saved registers are stored away somewhere in some data structure, and then it's over, and then it returns to the kernel, and then basically the kernel can actually call the switch. Will run another process. And when that process, when the kernel wants to take the process away from that process, it will do an upcall again to the user process saying like, "Hey, now I want to time you out. It's the end of your time slice. You're done." Right? And in fact, in the extra kernel interface described in the paper, you explicitly allocate time slices. There's basically a big array of time slices, and when you want to run as an application, you call the system call to give me a time slice, and that gives you a time slice. You can get the same time slice over and over if you wanted to, sort of amortize the overhead of the system call. But so there's a very, very low-level interface, right? And where the library operating system is almost as close to the processors you can get, except for this sort of multiplexing idea. Why? And so the risk, of course, is that if you do that, then when you do the upcall to user space, and the user space program says, "Great, you want the processor back? I'm just not going to give it to you. I'm just going to sit there and just use it. Why should I give it back?" My application is more important than the other application. I'm going to keep running. And so the extra kernel, and this is the piece that we have not implemented in JOS, but then the good extra kernel would have to do. There has to be a measure for basically dealing with misbehaving applications. Right? And in the paper, we call this revoking resources. And there has to be a protocol that if you don't give your resource back when asked, then you get slammed. And so the way in the extra kernel story is basically you do an upcall, say please give the resource back. You get some time to do the switch. If you don't do this switch in that particular point in time, the kernel just takes you away, kills you. That's a little bit of a regressive matter, but at least that will get the job done. Make sense? And so you might wonder, okay, so this interface, if you compare the extra kernel interface with the Unix interface, is completely different, right? Because what are the system calls, the equivalent system calls in JOS? Rattle this off. Right? You implemented most of them by now. So think about Spawn. Right? That's a good way to think about what do you? How many people are done with Spawn? Okay, good. All yours. I don't think that's a good fair question to ask. But you do know what the system calls are. So what other system calls are available for multiplexing this? Yeah, go ahead.
Sys-exafor?
Yeah, sys-exafor, correct? And what does sys-exafor do?
Gives you a sort of a blank slate process.
Yeah, it's just basically an entry in the environment table, correct? And there's not much in it, correct? In the environment, right? You still have to build up the rest of the process using those primitives, correct? Like, so what's the VM interface? Is that similar to, it doesn't look like exec and sbreak at all, right? Like, what's the VM interface look like? The system calls for.
Yeah, there's system calls to allocate pages to map pages and to unmap pages.
Yeah. So in fact, in your kernel, right, you actually allocate physical memory, right? I mean, allocate page. You can't do anything with it, right? Because everything runs in virtual memory enabled. But you can ask the kernel when you construct a library operating system, please give me a physical page, right? And that point, that physical page belongs to that application, and the only thing the application really can do with it, of course, is actually insert it in its page table. Right? But there's an explicit call to actually get the physical page, which in another, like in a microkernel system or in a monolithic system, that's not there. But there's enough primitives, correct? Like both the very low level interface is enough to actually build up, these higher level primitives, right? Like spawn basically takes exo4, correct? Alloc page, map page, and a couple other things to basically build up a complete user level process that actually implements the same thing as exec4 does, right? Now, once you implement in the lab, you don't really have to deal with the resource replication issue, right? There's enough complexity as it is, but if you were to do this correctly, you would have to implement, there would be system calls to basically register a context switch upcall like the page fault upcall. Right? So you, for example, you can implement, spawn all the user level because like page faults are redirected straight up to user space, where you can actually do something with that. So that interface is way lower level than these interfaces. But once you have it, like, so what can you do? What can you do the VM tricks that we probably have erased? Yeah, or a list of VM tricks here, correct? Can you do those in user space? Using extra kernel? Can you do shared memory? Passing memory data through shared memory? Yeah, totally you can. Right? You allocate a page, physical page, then you ask two different processes to map that page into their virtual memory system or their virtual page tables. And now, currently in JOC, you don't really deal that much with security, right? It should be the case that not anybody can actually map that physical page into their VM system. There should be some checking that you actually own that page. You can totally imagine how to implement that, right? So can you do copy and write? Well, you have to do it, right? It's not a question of can you do it, you have to do it, at least in the labs. And so all those tricks, that the kernel developers internally use are clearly exposed to the usual lab that you play around with. And so even on the virtualization side, there are cool things you can do. So for example, one trick, it's pretty clear on the VM side, correct? There's a lot of things you can do because you're actually doing them in the labs. But on even in just as a strict, slight difference between the extra kernel described in the paper and the extra kernel you implement, in the case of context switching, in the system as described in the paper, as I mentioned, there's an upcall from the kernel to the user saying, like, please give the process away. Please give me the process back, the processor back, right? So there's an upcall or switch. And you can do all kinds of cool tricks in a switch. For example, you could decide not to save all registers because you don't care about them. Now, in the x86, there are 8 registers, so this is not a big deal. But like on other processors, like RISC processors, they tend to have many more registers, and so you can get like a lot of performance optimization by not saving every register. You don't need to save them. Another cool trick you can play, correct, which actually the kernel internally, x86 internally plays. Let's say you're having user level spin locks. So you have an implementation of require and release. Let's say your application is multi-threaded, right? So it runs on multiple cores at the same time, and use spin locks, maybe for shared memory page to coordinate some of the access to their internal data structures. Now, in a normal kernel, or a monolithic or a microkernel, if the kernel decides to take the processor away, it could be the case, right, that that user level application just happens to be in this critical section, in the middle of the acquirer, right, holding the lock. So if the kernel takes the user level process away while the user processor holds the lock, can any other threads make forward progress? No, right? So they're also wasted, basically. So by taking away, the processor from the one thread that actually is crucial in making forward progress, basically the kernel is delaying every other user level thread, right? Now, in the case of an extra-kernel, this is easy fixable, right? Because at some point there will be the switch opcall will come. Switch opcall will come. The library operating system can say, aha, I'm in the middle of a critical section, right? So please delay, I'm not going to give you the processor away, but I'll give you very, very soon, and as soon as I'm done with the release. Okay? So in that sort of a time budget that you get to finish the switch, and presumably sufficient to actually just finish a critical section. Make sense? Now, how does Linux get around this problem? Right? Why doesn't all user level programs on Linux die in terms of performance when one of the threads actually gets context switched out? Same is true actually in x86. The reason that this is not a big deal is because for every user level thread, there is a kernel thread. And so, the kernel actually is ultimately aware actually of what actually the structure is in user space. And that's the way you get around that problem. Right? But in the extra kernel context, the kernel doesn't have to be aware at all of how user space is organizing things. So in Linux, if you implement your own thread package, it's actually pretty hard to actually do a good job at that. Unless you allocate a kernel thread for every thread that you're creating. Make sense? So you sort of get an understanding what the differences are between these different organizations. Okay, so, well, we're clearly established they're very different now, hopefully. And so let's talk a little bit about these sort of goals. And let's look at extra kernels. Well, first point, are they easy to develop? Well, not if you have to implement work with a low-level interface, right? But like in the microkernel case, presumably there will be some library operating system that implements most of Linux or most of Unix, like the way your library operating system implements some subset of Unix, right? But then you can use your own library operating system if you do want to handle with you want to deal with the low-level interface. It's actually the least possible. Can apps use hardware resources? Absolutely, right? Because the kernel exposes any hardware resource. In fact, there's no claim that it actually is portable across hardware platforms. Are they isolated in multiplex? Well, in principle, they are. If you get all the machinery right, that basically the paper shows that you can actually do it. Few kernel crashes. Well, basically the extra kernel has really no point of view on this particular topic, right? Because a lot of your code is going to be sitting in the library operating system. If the library operating system is buggy, then that will be exposed to the application. Right? So maybe there's a story about splitting library operating system in smaller pieces or running them in different address space. You can think about that, but that's not, certainly the paper doesn't address this point at all. It's just basically the same properties, if you will, as monolithic kernels, because somewhere all the code has to be implemented. It's the same functionality. If you implement spawn in the kernel or user space, roughly the same amount of code. Can kernels evolve? Well, the kernel may not be could in principle evolve very rapidly because all the abstractions are sitting actually in library operating systems. Right? There's not much to the kernel period, right? Because it just exposes whatever the PC platform or, in the case of paper, whatever MIPS platform is exposed to. Does that make sense? So now you might ask, in practice, what actually happens? Which organization, and this is the key question, is the better one, right? And this is where all the, the wars online are, and the debates in OS groups, and somebody pointed out the link to the famous sort of debate between Tenenbaum, who's my former advisor, actually, and Linus, right? And they were going bang, bang, bang. against each other. Where I think Tenenbaum was saying, like, you would fail my OS class if you were taking it, because who would implement a monolithic system in the early '90s? That's just stupid. And so what, and of course, Linus is perfectly capable of defending himself. And so if you're interested, you should read that whole discussion. But it does raise the question of, like, what does actually really happen in practice, right? And I think in practice, people take a very pragmatic view to this whole topic, because if you look at Linux, it's not one way to look at it. You can say it's a purely monolithic system. And the answer is yes, it's true, but not everything runs actually in the kernel. Does Linux have user level servers? Yeah, the X server. Yeah, the X server is a user level server. And any others?
You did?
Yeah.
You did?
It actually turns out like a lot of little servers that are using, right? Of course, like your DNS server runs in as a server, right? It's not implemented in the kernel. So in fact, if you look at it, there's a ton of servers actually in the Linux system. Maybe not the ones that the microkernel guys want, but they're at least user level servers, correct? And how do they communicate with each other? Using IPC, in the same sort of microkernel style. So it's totally possible, right, to split off a whole bunch of things into servers. Now it is true that in Linux, for example, most drivers sit in the kernel space, right? And often it's the drivers where the bugs are, because for every hardware device, you have a different driver. It's written by somebody who knows who. Probably some hardware developer that was implementing the hardware platform, probably not the best programmer, and as a result, buggy device drivers. And there's quite a bit of work in the Linux community on trying to put device drivers in user space, but most actually stick them in the kernel. So how about the low-level, like the whole extra-kernel philosophy, exposing low-level interfaces or like allowing applications to do VM tricks? Well, it turns out Linux actually allows you to do a mapping of pages and mapping of pages, and actually you can catch page faults, right? So that it's not just a Unix interface. It also has a whole bunch of bags of other calls that allow you to get more control, right, over lower-level resources. So if you take a pure view and say, like, well, one way to think about this is that basically Linux, right now, so most monolithic systems today are not purely monolithic. They just don't implement just positives. They implement whatever's necessary for application developers to get the job done. And if it's necessary for application developers to have map and unmap, or page fault, they'll all put it in. Right? And so the kernel interface gets bigger and bigger over time, but whatever. That's what people need. So they, I think, particularly in the Linux community, very clearly responds to what actually users need, and whatever users need, they'll implement. Now, if you have to start, and so I think then you could still argue the question, why not still big kernel? Why not just reorganize the kernel so that it actually is a microkernel system, right? Like what? And why doesn't Linux sort of take a step back and say, like, okay, good, like, well, we think microkernels are wonderful. Of course, you're never going to get that message through to the Linux community, but let's assume you could. And you're going to say, like, okay, I'm going to change Linux into a microkernel. It should in principle be possible, right? Because you can do what the microkernel guy said, like stick the file server in the visual process, et cetera, right? So the code is there, you just have to reorganize it a bit. Why not do that? Yeah, it's 10 million lines of code. Well, more than 10 million lines. That's a lot of work, right? And what could you do instead, in the meantime?
It's probably less work to just support the new devices that come out instead of just
they can make users happy by implementing the system calls they need. Because most application developers are not going to care one bit whether it's a monolithic system or a microkernel system, right? They want to write their applications and they want to get the job done. And so you can spend your time reorganizing your system or actually delivering code that actually people want. Building new, writing new devices. So it's not that easy. So if you're pragmatic about this, but you have that choice, then presumably what you do is maybe you'll rewrite a little bit and you try not to make the kernel bigger and bigger and bigger, but your emphasis is on actually probably implementing new features, right, instead of rewriting. And rewriting tens of millions of lines of code is just like a ton of work. Right? So what if you start from scratch? What should you do? So you have no constraints. Like in cases like Linux, they have an excuse, right? They already have tens of millions of lines of code that they're already got, they have since the beginning, and so changing that back into the microkernel seems a lot of work, and maybe you're not too excited about doing it. But like, what if you start from scratch?
Don't start from scratch, just use something that's already there and invest in features.
Okay, that's proven in one answer that a lot of people follow, right? But I think this is why you see microkernels in other spaces, not in the desktop space and not in the server space, because in there you can start from scratch. Right? If you do embedded devices or embedded systems, then you don't have to support Unix, or at least not most of it, and so it's much easier to get off the ground. But even then, you might actually use. If you look at smartphones, which operating system has succeeded? Which organization has succeeded so far? I should be careful because maybe it will change. It's a monolithic system for microkernels. Monolithic, right? You're running Linux on your phone. That's what the way the world is. Like 10, 15 years ago, people were thinking, oh, it's never going to happen. Right? Like your phone is not going to be powerful enough to run tens of millions of lines of code. But that's not the way the world has panned out. Actually, they're running Linux. Or iOS, which is some strange mixture of microkernels and monolithic all in iOS, it's an interesting story. It's based on the Mach 2.0. Okay, Mach is a microkernel out of CMU, late 80s, early 90s, and it was sort of organized. The first, one version was sort of organized like this, except that all of Unix was implemented in one process. Mach 2.5. But then that was and so Mach 3.0, they tried to split this all up, and it actually was not particularly good for performance. But Apple actually picked up Mach, and so if you look at core kernel for macOS, then actually on the bottom there's still the Mach sort of microkernel. And so there's still IPCs and all that stuff going on, except the way most of I'm going to make this a little bit misleading, but like most of macOS basically includes the kernel, runs the kernel plus the usual level processes also in the kernel, so it's easy to coordinate the different servers between them and get good performance. So you can think about the kernel organized in the microkernel, except everything is still the whole operating system is still sitting in the kernel space, most of the kernel. And partly because of performance reasons, partly because it's actually hard to get sort of the split to really work out. Any questions? Yeah.
So recently, operating systems have been able to catch driver errors, like when the driver crashes and just restart the driver. How does that work if the driver isn't running?
So this is indeed sort of something that lots of people have been playing around with, and I think the microkernel guys made most progress first on, where like if the driver runs a user space and then it just fails, you can just have a separate process, like the watchdog process, that just sees, like, hey, is the file server still running? Is the file server still running? And if it's not running, then you start it over again. For most device drivers, it works perfectly because the device drivers don't have any internal state. Right? You just restart it. And you're hoping that basically, when you restart it, like sort of cleans out whatever buggy state it was in, and it will keep running for a long time to come again. And basically, in principle, you can do the same trick in a monolithic system too, right? You can have an internal kernel thread, the watchdog thread, it just makes checks if like there's a, you have to sort of encapsulate the device driver as a runnable thing. But in most kernels, that's sort of like, there was already a thread there to like receive interrupts, and so if you make that a little bit more of a process, then you can actually do exactly the same trick. Yeah.
So, are there any giant OS design decision level changes between Linux and Windows, or are there any big things that Windows does differently?
Yes, kernel APIs are different at some levels, but at the level of discussion, they're sort of identical in their ability to make. In fact, there was some push right for Windows. First of all, it's hard for me to comment much about Windows because I never looked at the source code. I don't, it's not publicly available. But there was at some point a push, indeed, also having some sort of microkernel-based organization, right? And that basically sort of turned out as sort of a simple story as macOS, where internally the kernel is better organized, but still running most of it is running in kernel space. But also a lot of services, like in Linux, are implementing user space. But it's a big kernel, as opposed to bigger than Linux. And it has many, many more system calls than Linux does. So then what makes the question, what I think is fascinating is like, this kernel crash issue, right? If you have so many lines of code, how is it possible that these lines of code are correct? And they're presumably not correct, but nevertheless, I don't know what your daily experience. Does your kernel crash a lot? It used to, right? That's true, right? Yeah, I mean, like 10 years ago, like the blue screen, right? Was pretty common. But how often do you see that today?
Once per day.
Huh?
Once per day.
Sure. Maybe you have pretty hardware. Mine at least anecdotal. It seems to actually appear a lot less than like 10 years ago, right? And so something that the monolithic kernel people have done is like figuring out actually how to produce operating systems that have tens of millions of lines of code, and they work. Most of the time, they work. That's in some sense an sort of impressive engineering effort. All right, so hopefully this sort of, now you go online and you read over microkernels or monolithic kernels, you can hold your own, you can choose. I don't really care which position you take, as long as you can argue either one end of it. But probably if you build a kernel from scratch, you probably should start with microkernel, but it's a good point. Maybe you should never build a kernel from scratch. Start with something that already works. All right? Have a Monday.